All right, so 8.1 is on the square root property and completing the square. So kind of like we were doing with the square roots and solving, we were squaring. Here, if we have something squared, we can take the square root to get rid of the square. And so in this case, x would equal the square root of y. However, there's actually two things that when you square it will equal something. For example, if I said x squared equals 9, you could either have 3 being squared there, or you could have -3 being squared. So -3 times -3 will also give you that positive 9. So there's two answers, two values for x that will give you a true statement. And so the way to account for that is we always put a plus or minus when we take a square root. So the most basic is, well, what squared is 81? And you might go, oh, 9. 9 squared is 81. But there's two answers. And one of the cool things with polynomials is that the highest exponent tells you how many solutions you're going to have. You might have it twice. That's called multiplicity, but it still is always going to add up to this highest exponent. So we should have two answers. And so it turns out that it's going to be positive and -9. So when I take the square root and I take the square root, I need to add in plus or minus, and then I can simplify the square root of 81 to be 9. So I have plus or minus 9. Always check your work. So 9 squared is 81. Yep. -9 squared is 81. Yep. Number 2 has a quantity, but we treat it the same. This will be x plus 3 because the square root and the square cancel. Don't forget your plus or minus. And so that's what this little reminder up here was for. When you take a square root, don't forget your plus or minus. Sometimes people make two equations. Sometimes people like doing it all at once. It's up to you. You can write 5 and then make another equation with -5. Or you can just say 5 minus 3 is 2, and then -5 minus 3 is -8. And then check your work. 2 plus 3 squared is, that'd be 5 squared, which is 25. -8 plus 3, that's -5. -5 squared is 25. It's also true. So I do check them. Sometimes I just check them like in my head rather than literally writing it out. Then let's talk about this one where when I take a square root, it's not a perfect square. So we're going to have to make use of the properties that we learned earlier about simplifying square roots. So look for a square factor. In this case, the highest one is 4. Or make a factor tree and you'll see you have 2 2s and a 5 left over. So this is 2x minus 3 equals plus or minus 2 root 5. I want to solve for x, so I'm going to add 3. I'm going to undo my addition or subtraction. Now here, when I add this, these are not like terms. So I'm going to have to say 3 plus or minus 2 root 5. Or I could say plus or minus 2 root 5 and then plus 3. But we typically put, again, the more rational part in front and then the irrational or imaginary part second. And you'll notice that this ends up being equivalent to what you get if you use the quadratic formula. And when you use quadratic formula, it will be in this format where it's the square root part second. So now I need to divide by 2. So I have 3 plus or minus 2 root 5 over 2. And those coefficients don't all have a common factor. So that would be my two answers. The 3 plus 2 root 5 over 2 and the 3 minus 2 root 5 over 2. So you have two answers because of the plus and the minus case. You can write this as 3 over 2 plus or minus, and then the 2's can cancel, plus or minus root 5. But this is actually a much, I don't know, nicer way, and it's less likely that you make mistakes if you just leave it like that. So I'm going to project a few others to just briefly discuss. Number 4, I took the square root to get rid of the square. So I did on that side. So then I put my plus minus. And this had a negative. And that's okay now because in lesson 7.7, we learned how to deal with the square root of a negative. It's not a real number, but it can be simplified in the imaginary number system. So it would be 5 from the 25 factor, I from the -1 factor, and then root 2 from the 2 factor. Okay, now we undo addition or subtraction. Again, not like terms, so just stick it in front or in the back, but preferably in the front. And then undo your multiplication by division. Now, each of these was divisible by 5. So if I divide each of them by 5, each of the coefficients by 5, I get my answer. You could also have factored out a 5. And then simplified, and then you'd have your -1 plus or minus I root 2 all over 2. So when you're simplifying it, it is the same process that we did with polynomials where you factor and cancel, but you can also kind of factor it in your head and by saying, okay, I need to get all of the terms divided by a common thing. Again, you can divide each of these by 2, and that would be another way of expressing it. All right, this is one where it's not an isolated square. So I would first isolate. So I'd add 10 to both sides so that my square thing is isolated, and then I'd take the square root and simplify as much as possible. So we talked about square root of negatives being imaginary numbers. 40 is 4 times 10, so it's 2 root 10, and that negative, again, gave you the imaginary. Just don't forget your plus or minus. You should have 2 answers. Okay, so the next part of this section, 8.1, is on completing the square. And so completing the square, you are trying to write something as a perfect square. So something squared or something squared with either a plus or a minus. And so in order to get a perfect square, when that's expanded, and we've done this before, you end up with a squared plus 2ab plus b squared when you FOIL. F, the O, and the I, and then the L. If it's a negative, it'll be minus 2ab. But again, a negative times a negative for your L will still be positive. So the difference is the plus and the minus if it's a plus or a minus. So another way of kind of reminding us of how these work is if I gave you an expression like this, what would make this into something that is a perfect square? So in other words, if I use my X thing, what is the C that gives me a B of 14? That these are going to be the same number because we're trying to make a perfect square. So it has to be something plus or minus something squared. So we know that the X times the X will get us the X squared. But what goes here? And the A is 1, so it's just a simple what works to make it add a 14 where they're the same. So if it's the same, 7 and 7 are the same, they add a 14, they will multiply to 49. And so it would be 49 here, and it'd be X plus 7. And then X plus 7, so X plus 7 squared. So the generic way of handling that then, the rule essentially, is that you're going to have your B value here, just like before. So A, B, C, when it's in standard form, the coefficients are A, B, and C then. And you're going to take that B, and because you want it to be the same and add, they have to be split. It has to be split in half. Like 14 has to be split in half for these to be the same. And then what we do is to find the C, these are supposed to be multiplied to give you this. So when we multiply that, we get b over 2 squared. So that is the generic equation. So it'll end up being x plus b over 2 squared. Or if this had been a minus, then it would be a negative, but then a negative times a negative will still give you a positive. So if it's, say, positive, what we can do is we can take half of it, that's the b divided by 2, and then we're going to end up squaring it. So it's going to be b over 2 squared is what completes the square. So 6 divided by 2 squared, that's 3 squared, that's 9. Or you could say 36 divided by 4. You'll get 9 either way. So use the rules of exponents or order of operations, you're going to get 9 either way. And so that is x plus 3 squared. 9, 6, 3, 3. X plus 3 squared. When it's a negative, it's still the same rule. So it's your b divided by 2 squared that completes the square. So negative 10 divided by 2 squared. Negative 5 squared is 25. In other words, your b was here. These had to be the same. They're negative 5 each. To get you the negative 10, that multiplies to positive 25, which we have here, positive 25. It is x minus 5 times x minus 5, so it's x minus 5 squared. So this plus contributes to this plus, this minus to this minus. So what if it's not got a blank and you're not just trying to write the perfect square? What if you're actually trying to use this to solve for a variable? So you want to complete the square, and we liked having it so that it was x squared plus or minus some x's plus a blank. So this, when I do this, it's not a perfect square. It doesn't work out that way. So what I want to do is subtract 5. Oops, that's a minus. I want to complete this as a perfect square, and it will be equal to negative 5, 0 minus 5. But if I add something to this side, I have to add it to this side. So to keep these equivalent, I need to make sure I put blanks for both. So when I complete this square, I keep the expression, or in this case, sorry, equation, equivalent. So the process is in your textbook. I changed step 1 a little bit maybe. So it's a generic, you just subtract your constant from both sides, and then you'd fill in the blanks for both. So that's kind of my setup. So now I'm going to do half and square. So I'm going to do negative 6 divided by 2 squared. Negative 3 squared is 9. It goes there. But I do to one side, I do to the other. So then, now that I completed the square, I isolated the x's, I completed the square. I can write it as the perfect square. And if you're not sure what it is as a perfect square, there's 2 ways to go about it. 1, it's always half of the b. Option 2 is to make your little x and realize it's negative 3. That way. All right, so now I've written it as a perfect square. So I can use the square root property that we just discussed on the prior pages. We can take the square root to get rid of the square. When you do that, don't forget your plus or minus. The square root of 4 is 2. We've taken the square root, so we don't put a root symbol around there. Okay, let's get x by itself by adding 3. So we have 2 plus 3 is 5, and we have negative 2 plus 3, which is 1. So those would be my 2 answers. You can solve quadratics by potentially factoring. This one would be factorable. You could solve it by quadratic formula, which we'll talk more about coming up. Or you can use the square root method, but you'd have to complete the square first since this wasn't a perfect square. So there's lots of techniques, and part of the whole point of these couple sections is to show you all the techniques, because sometimes one is more efficient than another. And this completing the square will come up when we talk about circles at the end of the course, as well as when you do ellipses and hyperbolas, and it allows you to do the square root method for solving these quadratics. It's also great for just talking about perfect squares. So let's do a few completing the square problems together, and then I'll project a few as well. So let's do, let's do number 10. All right, we want to isolate the x terms. So we're going to have x squared minus 10x plus blank. To get that blank there, I end up now doing 20 plus blank. So I've added a blank to both sides, and I've got it so just my x's are by themselves, so I can complete that square. So I'm going to take half of my b and square it. What I do to one side, I do to the other. Okay, this expression is the perfect square, x minus 5. I'm writing it as a perfect square so I can use the square root method for solving. And then that is 45. So to solve that, I'm going to get rid of the square by taking the square root. So I'll have those cancel out. X minus 5 equals plus or minus, because we're taking a square root, and 45 is 9 times 5. So this is the same as 3 root 5. So it's going to be plus or minus 3 root 5. Then we need to add 5. Again, the plus 5 can go in front or the back, but common standard format is the front. So it's 5 plus and minus 3 root 5. These cannot be added to 8 because that would not be following order of operations. You have to do your multiplication before you do your addition, and these are not like terms, so you can't add them. So there's two ways to think about why that can't be added. Two answers, 5 plus 3 root 5, and then 5 minus 3 root 5. In XYZ, you'd actually have to write it as two separate things. They don't have a plus minus symbol. So those would be your two answers. So I'm going to project a few others. So here's number 8, and I isolated the x terms, complete the square, half of this and square, and then you can always take half, or you can say, well, what gives you the 16 and adds the 8, 4 and 4, so it's x plus 4 squared. Here you'll end up with 6, which cannot be simplified, and so it's just going to be negative 4 plus or minus root 6. We did one just a moment ago, which was this one, where your root could be simplified. Let's look over here. This is one where there's a fraction, because your b is odd, so when you divide by 2, you end up with a fraction. So it's going to be 7 divided by 2 squared. 7 divided by 2 squared is 7 squared, 49, over 2 squared, 4. And so then you need a common denominator to add fractions. So I rewrote 3 as 12 fourths. So 12 fourths and the 49 fourths gives me 61 fourths. This is, again, always half. And so now to get rid of the square, I square rooted. When I took the square root, I put the plus or minus. Root 61 does not simplify, but this expression, it's root 61 over root 4, and the root 4 can become 2. So it's root 61 over that over 2. And then subtract 7 over 2, 7 halves from both sides, and put it in front preferably. And then if you notice, you have a common denominator, so you can put it into the more typical format that we have over here. Common denominator you can add or you can subtract, and that's what you get. 11 is another one with fractions. And I'm not going to spend too much time on that because we just did one. But I will project it, and if you want to pause and look it over on the recording, that's fine. I'm not going to do many examples where the A is not 1 because it's all much more involved. So because the A was not 1 here, we had to divide both sides by 3 to get it to be an A of 1. You'll notice that that's when I started doing the completing the square, because that method only works when A is 1. The leading coefficient of the quadratic is 1. There is a way to do this where you factor out and you deal with the factors, but this is the cleaner way for right now. And that case of A not being 1 is definitely more challenging. There's examples in your textbook, and we will not be focusing on that. You'll have a few homework problems to practice it, I believe, although I may have gotten rid of them. I think I may have gotten rid of them.